Hey folks, this is Scott Weingart, and you're listening to the emcrit podcast.
All right, folks, part 3 of acid base. This is going to be a quick one. Before we start, let me tell you about an event. This is the Columbia Neurocritical Care Conference. I speak at this conference every year. It's organized by a friend of mine and an incredible neurointensivist, Stefan Mayer. They're doing it in New York like they do every year. It's June 14th to 17th. And the nice thing about this is there's a strong focus on emergency medicine. So I'm going to put the link to the website and check it out. You could also just put into Google Neurological Emergencies Columbia Symposium, and it's going to come up. Check it out. I'd love to see you there. So that'll be in the show notes. Acid base part 3. So I gave you a problem last time. It looks something like this. And a lot of you had written in saying that you were able to solve it easily using the emcrit method, which I love. So let's go through it. This is kind of a easy problem. There's no tricks here. So let's just run through the list. And you could print out the problem and this acid base sheet if you don't have them and follow along. So step 1 is to get labs. We have labs. Great. Step 2, look at pH. pH is 7.05. I could pretty much say this patient has a acidosis. All right, that's easy. Look at the blood gas CO2. Blood gas CO2 is 14. So this patient has a respiratory alkalosis. And we'll decide why in just a bit. All we have done so far is establish they have it. Step 4 is to calculate the strong ion difference. The difference primarily between sodium and chloride in this case. So when we look at here, we have 122 on the sodium and we have 88 on the chloride. So the difference between them is 34. So our strong ion difference is 34. And we said normal equals 38. So this patient has a 4 millimole per liter strong ion acidosis. So essentially what's happened is their chloride is high relative to their sodium. And as a result, that's making them a little acidotic. This is a very mild situation. 4 is no big deal. So you have a patient with a mild strong ion acidosis, but we'll put that in the back of our minds as contributory to their acid-base situation. All right, step 5, look at the lactate. Lactate is 0.5, which is totally normal. Great. Now step 6, the difficult one, the SIG. So the SIG calculation, let's run through it here. So the first part of the SIG calculation is the base deficit. And we said the base excess is minus 18, so the base deficit, 18. 18 is what we need to fill. All right, so the first thing was we see if the strong ion difference is contributing. So we add the strong ion difference minus 38. So that would be plus 34 minus 38 equals minus 4. So 18 minus 4. And now we have so far in the equation 14, right? So we could put the 14 there, go to the next part. Next part is to correct for albumin. And it's 2.5, 4.2 minus albumin. We said albumin's 5.2. So now it's going to be 2.5 times minus 1. So it's minus 2.5. So now we're down to 11.5. And then the last part is to subtract the lactate. So it will be 11.5 minus 0.5 equals 11. So 11 is our strong ion gap. All right, now a strong ion gap of 11 is high. What we have to figure out now is why the patient has 11 of unmeasured anions, of unmeasured acid. And in this patient's clinical scenario, high sugar, everything looks like DKA. Chances are that 11 is filled with ketones and keto acids. All right, so we feel pretty good about that. We go to step 7, think about compensations. I don't even bother. One question was sent in saying that the CO2 is a little bit lower than expected. What's going on? Does the patient have an additional primary respiratory alkalosis? Chances are the patient probably just was breathing a little more rapidly while people were getting a VBG on him. This is why I don't really buy into this respiratory compensation as being all that important. I just look at the direction. The CO2 is going where I expect it to go. I'm feeling pretty good. All right. If you had a high sig with no explanation, step 8 would be calculating the osmolar gap. I'm not going to bother right now. I'm pretty sure of what's going on with this patient's acid-base status, but certainly if you didn't know, you could calculate an osmolar gap as well. Now, let me show you something here. Let's say you didn't have the blood gas. What you could always do is subtract the actual bicarb from 24. And let's see how that looks. So let's say we have 5 bicarb here. You could take 24 minus 5 equals 19 and just use that as your base deficit. All right, so this patient now, for the purposes of this, would have a base deficit of 19. And then you could just go on with the rest of your equations, and that works pretty well. So that's one way of dealing with it if you don't have a blood gas, is you just subtract the actual bicarb from 24 and use that as your base deficit. All right, so that was problem 1. Problem 2, same patient, and this will be in the show notes if you want to print it out. Same patient, except now you've had him for 4 hours and you've treated him, and now you have these new values. All right, so let's run through it from the top again. So step 1, get labs. We got our labs, great. Step 2, look at the pH. All right, the patient's pH is 7.05. That's still really low. And in fact, you know, the team came down and saw these labs, and you were trying to put the patient on a regular bed, and they are freaking out. They want the patient in ICU. They're like, you haven't done anything for this patient. His pH hasn't budged a bit. What the hell are you people doing, thinking this patient could go to a regular bed? And while you sit tight and say, no, this patient's doing great. What are you talking about? And you're arguing back and forth. But you're going to use your superior acid-base knowledge to show them why this patient's no longer sick, even though their pH hasn't really changed a bit. All right, so let's run through. We got our labs. We look at the pH. Patient's still acidotic. We look at the blood gas CO2. That's completely normal. That's not a problem. Let's calculate our SID. All right, so it's 132 minus 112. 20. Wow, that's quite high. The patient has a strong ion acidosis, what we would also call a hyperchloremic acidosis. All right. So what happened? Well, you probably gave the patient a ton of saline to resolve their DKA. And that's what happens when you give a ton of saline. And we'll talk more about that in episode 4. All right. So step 5 is look at the lactate. Lactate 0.5. That's just fine. All right, now let's get to the fun part, calculating the SIG. So SIG equals base deficit, base excess of minus 18. So we have a base deficit of 18 plus their SID minus 38. All right, plus 2.5 times 4.2 minus albumin. All right, so why don't we do that part so far? So we have 18 plus minus 18 plus 2.5. The albumin is 3.2, so that's 4.2 minus 3.2 is 1, so plus 2.5. And what do we have so far? We have 0 plus 2.5. And so the last part is to add, subtract the lactate, so minus 0.5. And now we have a SIG of 2. All right, now a SIG of 2 is within the normal range. Probably has just a bit of residual ketones hanging around. And So step 7, we don't have to worry about respiratory compensation. Step 8, we don't have to worry about the osmolar gap. So what do we have? We have a patient with an almost entirely chloride-filled acidosis. Maybe they have just a few ketones still lingering about, but this is a patient who's doing great. Eventually, their kidneys will get rid of that extra chloride, and this patient's going to be fine, and they don't need to be put in a unit bed. This is a very different acidosis now. Now we've taken a strong ion gap acidosis or an anion gap acidosis and converted it to a non-anion gap acidosis. This patient just got a whole bunch of normal saline. Now, why did I also want to show you this problem? Well, it's time for the reunification of Henderson-Hasselbalch and this quantitative method I'm showing you. Let's say you wanted to do your pure Henderson-Hasselbalch approach, all right? So I guess you'd start off with the anion gap, and the sodium is 132 minus chloride of 112 minus the bicarb, all right? And what you'd get is 10, all right? Now, if you stop there, Henderson-Hasselbalch is going to be inaccurate, and the worse off the patient is, the more inaccurate it's going to be, because you're not accounting for chloride, you're not accounting for albumin, and you're not accounting for lactate. So right off the bat, I tell you, you got to correct for the albumin. You correct for it the same way, same formula, 2.5 times the normal albumin minus patient's albumin. So in this case, it would be 2.5 times 4.2 minus 3.2. That's 1. So you get 2.5, and you add that to your gap. So now it would be 10 plus 12.5. So now it would be 10 plus 2.5 equals 12.5. That's your corrected anion gap. Now you've corrected Henderson-Hasselbalch's anion gap for the albumin. And if you do that, it is just as accurate as this quantitative method. Now, we look at that 12.5, we say 0.5 of that is from our lactate. So our final corrected anion gap is 12, and that's completely normal. So this patient has no anions, maybe they have a few, and so that's part 1 of using Henderson-Hasselbalch properly. Part 2 is you still got to go back and look at your sodium chloride difference. So your sodium is 132, your chloride is 112. It's 20 difference. We said normal, 38. Since this is lower, you say to yourself, this patient has a profound hyperchloremic acidosis. And if you don't do that, then you're missing out on a whole range of acid-base disorders with Henderson-Hasselbalch. So if you correct the anion gap for the albumin, and you actually go back and look at your strong ion difference by comparing your sodium and your chloride, then Henderson-Hasselbalch becomes just as accurate as the quantitative methodology. And any discrepancy in the fact that we got a very small sig with the quantitative and we got really no anion gap with this method is just because I've made these numbers up. In real patients, they correlate almost perfectly because essentially that's what your blood gas machines are doing when they calculate the base excess and base deficit. Is essentially they're just doing the same calculations we just showed you, and then pretty much everything else is the same. So there's really no great war between Henderson-Hasselbalch and the quantitative approach like I made out. It's just that people don't do all the steps necessary for the Henderson-Hasselbalch way. They get lazy. They don't do the delta gap. They don't do all those things you're supposed to do. So if you do it this way, if you correct the anion gap for the albumin and you look at the strong ion difference, you're going to be golden. Now, listener Mike wrote in. Mike got bitten by the quantitative approach bug. He's been reading a ton, and he discovered that most of the formulas for the quantitative approach are far more complex and annoying than the one I've put forth. And he asked, well, is there any literature to support this simplified approach? And there is. I didn't make this stuff up. This article in the British Journal of Anesthesia by D.A. Story, which I will put a copy of in the show notes, is actually going to take you through and show where the justification is for only using sodium and chloride for the strong ion difference, and for not correcting the albumin for pH, and a whole bunch of other simplifications that makes this possible to do in your head. Because I just worked out all those formulas. I don't do it that way. You can even see it. It's kind of, I have to think about it each time. What I do when I look at this stuff is, so I'd be looking, oh wow, look at that strong ion difference. That's a strong ion difference of 20. This patient has a pretty hyperchloremic acidosis because it should be 38. And then I look down at that base excess and, oh, that's minus 18. Well, I know the strong ion difference filled 18 of it. Now I'm to 0. But, oh, the albumin's low. Got to add 2.5. Now I'm back to a base deficit of 2.5. Oh, lactate. Subtract 0.5 of that. Oh, left with a sig of 2. All right, that's how I'm doing it in my head. I don't have to get a piece of paper, calculate this out. Once you get good at this stuff, it just takes a few seconds. Now, let's say you didn't want to do that. If you go to acidbase.org and choose their analysis module, they have a calculator that does all this for you. And it's pretty complex. They'll ask you for a lot of stuff, but you don't have to give them everything. You can just give them whatever you have, and they will give you all of this, and they'll do it all for you. So that's something to check out, is acidbase.org, the analysis module. All right, I'm going to stop there. There's going to be another bonus episode this week on finger thoracostomy, so I want to leave you guys time to listen to both. All right, so write me with any questions. Part 4 is going to be the fun stuff. It's going to be how this applies clinically. It's going to be about how fluids change the parameters of acid-base, and it's going to be about bicarb and when it's smart to use and when it's not. All right, so bye-bye.